So hello, everyone. So thank you for showing up to the second half of the workshop, and it's my great pleasure to introduce our next speaker. Shuran Song is an assistant professor in the Department of Computer Science at Columbia University. Before that, she received her PhD in computer science at Princeton University. Her research interests lie at the intersection of computer vision and robotics. And her work has received awards, including the Best Paper Award at TRO 2020, Best System Paper Award at Coral 2021 and RSS 2019, and the Best Manipulation System Paper Award from Amazon in 2018, and her other work has been finalist for Best Paper Award at ICRA 2020, CVPR 2019, RSS 2019, IRA 2018. She's a recipient of many awards, including the NSF Career Award, the Sloan Research Fellowship, and research awards from Toyota Research Institute, Microsoft, Amazon, JP Morgan, and Google. And it's our great pleasure again to have her give a talk, so go ahead.
Thank you so much, Daniel. It is my great pleasure to be here, and so nice to see everybody in person. Yeah, so today I'm going to talk about dynamic manipulation for deformable objects, and hopefully by the end of the talk, you think it is a good idea. Okay, so I think at this point of this workshop, I probably don't need to repeat the importance of manipulating deformable objects and why it is such a hard problem. But I do want to highlight one of the most fundamental properties of deformable objects that actually directly motivates our approach of using dynamic actions. That is, there are extremely high degree of freedoms. Right? So for objects like clothes or garments, they can easily be considered as have a near infinite degree of freedom. And what makes things worse is that among all these degree of freedoms, actually only a very small amount of those degree of freedom can actually be directly manipulated or controlled by the robots through contact. In other words, the system is often highly under-actuated. Right, so for example, if a robot just kind of holding a cloth, all it can control is a very small region of the cloth around the gripper, and the rest of the cloth is kind of just hanging there, and the system does not have any direct control over those auto contact positions. So as a result, because of that property, a lot of actions or action primitives that we designed for manipulating rigid objects is actually highly inefficient when we're dealing with deformable objects, because each time or during each of the interaction, the system can only manipulate or kind of affect a very small region of the class or the object compared to the total degree of freedom of the object. And apart from efficiency, this kind of quasi-static pick and place action also kind of limited the type of tasks the system can perform. Right? So for example, a system or a robot can never really manipulate an object that's outside its kinematic reach range. However, in contrast, we humans actually manipulate deformable objects in a very different manner. Right? So we often use very fluid and fast motion that fully leverage the dynamics of the object in order to quickly achieve our goal. So formally, we can categorize these two types of manipulation as quasi-static or dynamic manipulation. So fundamentally, what dynamic manipulation allows us to do is to leverage those accelerations in action, in other words, the dynamics in the system, in order to control those auto contact positions on the surfaces or the deformable object. Therefore, allows the system to obtain more control over the total degree of freedoms of the object. And I think this property is actually particularly beneficial for deformable objects or in general, a system that's highly under-actuated. So here are just a few quick examples of applying dynamic manipulation on deformable objects. So for example, we can fling a cloth to open it, or swing a rope, or opening a bag with active air. Right? So in all these examples, we can actually highlight the position on the object that's it's actually manipulated by kind of controlled by the system, but actually never really directly in contact with the robot throughout the manipulation process. And before we get into more details about those examples, let's take a step back and then think about this question. If dynamic manipulation is so well suited for deformable objects, then why we have not yet using it everywhere? So what are the main barriers preventing us from using dynamic manipulation for deformable objects? So I think there's three key challenges. So first is action complexity or the action sequence complexity. As you can imagine, for programming or kind of code up a simple pick and place action, you only need to specify 2 positions for pick and place, or like 2 unfactored poses. However, if you want to specify a dynamic action, we also need to kind of, in addition to specify these velocities or accelerations in action. Therefore, the policy or the algorithm that designed for dynamic manipulation really need to be able to handle this expanded action space. And another challenge is complex object dynamics. So as we know that objects' motion under dynamic action is actually highly influenced by their physical properties. And many of those physical properties is actually extremely hard to measure, especially if you consider deformable objects. Right. So that really requires the system or the policy able to actively adapt to those hard to measure physical properties on the fly. And I think the last challenge is about simulators or the sim to real gap, right? So I think by now the simulators for class or for deformable objects is still very far from perfect, especially when dynamics or dynamics actions are involved. So how to design a system that either can directly or efficiently learn from real world or robustly adapt this kind of sim to real gap is another big challenge. And into this talk, I'm going to kind of show some of the possible solutions for all those challenges through 3 of our recent work. And we'll start with a relatively simple task that's just kind of doing class unfolding. That's not really require very precise control, and moving towards more challenging tasks that actually has much higher requirements of precision and also is goal conditioned. So let's start with Flingbot, which is actually our first attempt of using dynamic manipulation for the task of class unfolding. So the task for class unfolding actually has a very simple objective. It's just trying to maximize the class coverage through interactions. However, just like many tasks in robotics, although the objective is very simple, designing or kind of developing a robotic system that's able to do this task efficiently and robustly is actually quite hard. Right, so here is an example of a 2-arm system that is trained to do this class unfolding task using pick and place actions. So what you can see is that it actually takes the system a very long time in order to make a very small progress. Actually, for a very long time, the class is still kind of in this compo state. And what's worse is that if the class being unfolded is larger than the robot's kinematic reach range, then the class will actually never be fully unfolded. So which means that if you think about unfolding your blanket in the morning, if the blanket is larger than your arm length, then you'll never be able to fully unfold it, which is not very ideal. Right, so, but obviously that's also not how we're gonna do this task, or like how human will do this task of class unfolding. So very likely what we're gonna do is something similar to this. We're gonna hold this class with 2 arms and then fling it with a high velocity in order to quickly unfold it. Right, so based on this observation, the key idea for Flingbot is actually really simple. It's just use high velocity 2-arm fling for class unfolding. So to implement this idea, we developed a system that learns how to unfold a piece of fabric using a sequence of pick, stretch, and fling action. So this the performance of the whole system or all the action primitives are directly measured by the class coverage that can be directly computed from the top-down camera. Therefore, the whole system actually can be trained end-to-end with self-supervision. So you can let the system collect training data by itself, and then it will just overnight improve its performance. So to make long story short, by the end of training, both in simulation and real world, Flingbot is able to reach 80% of coverage within 3 interaction steps, and at least for the class that we tested on. And it's also able to work on the class that is larger than its a physical reach range, and also generalized to class or garments has different geometrical shapes when it's only trained on rectangular class. So here is a more detailed comparison, and in particular, we compare to a baseline that's used only pick and place action. You can see that Flimba is able to fully unfold this class within just 3 interaction steps, where the pick and place baseline actually take much longer time to make progress. Even with significantly more interaction steps, it's still not able to fully unfold the class. And here is just another example of testing its generalization. Again, the system is only trained on rectangular class, but here we are testing it with a t-shirt with a quite different geometry and shape, but the system is still able to perform reasonably well. So I think throughout the process of developing Flimba, I think the most surprising thing we learned is that even without explicitly modeling the class state or using any complex learning strategies, Flimba is actually able to work really well for the task of class unfolding. And I think the simplicity of this approach really highlights the key takeaway for Flimba, which is the dynamic action is just really good for the task of class unfolding. But of course, I don't want to give you the wrong impression that Flimba is able to solve all the class unfolding tasks, which is obviously not true. So actually, one of the typical limitation, like failure case for Flimba is that when the class getting larger, significantly larger or heavier, the system cannot actually produce sufficient speed in order to fully unfold the class. So for example, here the system is trying to handle a long dress, and actually no matter how many times you try, because of the speed limit of the robot, it's never able to fully unfold this piece of this long dress. And also in those cases, in order to further increase the robot speed, it's either limited by the hardware or sometimes can even be dangerous if the system needs to operate around people. So in a follow-up work, actually, we try to address this problem by introduce additional aerodynamics. Right? So this system we developed is called dexterity with air in it. So what we do is we ask another robot try to control an additional air blower and learn a closed loop policy of controlling the direction of the air blower. And with the help of the aerodynamics, the additional aerodynamics, the system can actually easily unfold a large variety of class, including this long dress in this example. And another thing to note is that with this new formulation, we actually can easily replace all these 3 robots with some slow and cheap robot hardware, because now we no longer require the system to move in a high speed. And also the air blower, you can just buy it from Amazon with $20. And of course, error-based manipulation actually has a lot of other applications in addition to just unfolding class. Right? So here I'm showing you 2 other applications. One is trying to use active airflow to opening a deformable bag. The other is trying to blow the particles into a target area. And I think compared to those traditional contact-based manipulation, actually error-based manipulation has a lot of unique or complementary advantages that I think is still underexplored, and I think it's pretty exciting and interesting to think about. And go back to Flimba, I think another limitation that Flimba has is that it has actually very limited capability of handling goal condition tasks, or like, for example, achieving specific goals or configurations of the class. So for the whole system, actually what it's trained on or what it's only care about is the total coverage of the class, which means that all the configurations that you are seeing here is actually considered as equally good by the system, which is obviously not sufficient for many real applications that requires more precise configurations. So for example, if you want to fold the class, maybe only certain configuration is good for those tasks. So in the next project, we're gonna.
It's somewhere from the Zoom.
Okay.
Sorry.
No problem. Yeah, so in the next project, we're going to focus on actually another category of tasks that is much harder or much challenging, but also goal conditions. So what do we mean by goal condition task for dynamic manipulation of deformable objects? So here are 2 examples. One is trying to swing a rope and try to hit a target position in the 3D space. The other is trying to swing a class and then try to swing it in a way so that it's reached to a target configuration. Right, so in both cases, the goal is defined by the target keeping locations. So either it's on the tip of the rope or the corners of the clock. And in both cases, the goal are still outside the robot's kinematic reach range. Therefore, it still requires the system to leverage or make use of dynamic actions. So actually, in our earlier work, we have been purposely trying to avoid this kind of goal condition task because we just think it is way too hard, right? So basically, the combination of dynamic manipulation and the deformable objects make it just extremely challenging for the robots to precisely control its action in order to reach to an accurate goal. And in fact, it is a task that's even challenging for us or for people. So I think given a new rope or an unknown rope, it's actually very unlikely that you're gonna be able to hit a goal position within the first trial, right? So, but the good thing is that after a few trials, just like in this example, you typically will be able to kind of get closer and closer to the goal and eventually reach to the goal condition. So the question to think about here is, what do we really learn through this kind of trial and error process, right? Do we actually learn the mapping directly from our action to the full trajectory of the rope? I think probably not, right? So at least I don't think I can do this task. Or maybe we are trying to decoding the rope parameters through this trial and error process. I guess probably not either, especially for deformable objects, those parameters are actually really hard to measure or think about, like for example, nonlinear densities or mass distributions. So what we really rely on, at least we think, is a good intuition, or you can call it a prior knowledge, about how we can adjust our action in order to affect the trajectory to achieve the goal. Right. So for example, it's very easy for us to understand that if we swing harder, the rope will reach higher. Right. If we extend our arm further, the rope will also reach to a further location. Right. So in this work, we actually call this intuition residual policy. So our hypothesis is that the knowledge about the change is much easier to learn and also more transferable to different ropes or systems than the specific actions or strategies we learned. So to implement this idea, based on this kind of observation, we implement this idea called iterative residual policy. So at its core is the system actually learned delta dynamics. And what they do is that it will take in our observed trajectory and a delta action as input, and it will try to predict the updated trajectory after apply that delta action. And here the action, the robot action is actually represented by their target joint angle and the maximum speed. And then by sampling different delta action and then predict their corresponding trajectories after apply that delta action, then the system can select the best action that will get the system closer to the goal. And then it can iteratively refine its action until it reached the goal conditions. So note that the delta dynamics model, we actually only trained in simulation. And then as you can imagine, for this task, it actually has a huge sim to real gap. Right, so here is actually just an example of highlighting the difference when we are using the exact same rope parameters in simulation and real world. The trajectory is actually very different. But our hope is that the learned delta dynamics, especially its general direction, is good enough or generalizable to real world objects with different physical properties, even if the exact model is not 100% accurate. So here is a system in action. So at the beginning, the system will take an initial action that is actually the same for all different ropes. And then the distance to the goal is actually measured with the shortest distance along the whole trajectory. And then the policy will sample different actions and predict their delta trajectory correspondingly, and then select the one that actually has the smallest distance to the goal. And then this process will repeat until the system reaches to the goal or reach the maximum number of iterations. So that is for one rope. And in our evaluation, we try to evaluate the system's generalization capability to different ropes with different physical parameters. Again, in all the following experiments, we're going to show you the results of using the same model trained in simulation. And a lot of the ropes that we test on is actually quite significantly out of distribution. So for example, this long cloth actually has much higher air resistance when you actually swing it in real world. And this bow whip actually has a nonlinear density that the mass distribution is actually nonlinear. And for both properties, actually, we cannot directly simulate it in the simulation, in the simulator we have. Actually, we use a Mojoko simulator, which does not have, like, for example, air resistance simulated. So here I'm going to show you the resulting trajectories after the policy converges on different goal conditions. So you can see that the policy actually chooses to use very different action in order to achieve the same goal, just to accommodate different rope parameters. And we also test our system with many different scenarios. So for example, one of them is we're trying to test how well the system can adapt to online changes. So what we do is that we're going to test, after the system converge on a given goal on the rope, we're going to tie a few knots on the rope, which basically change the length and also the density of the rope. And we'll observe how the system is able to quickly adapt with respect to those changes. And we also test on the policy on different robot embodiments, which will basically change the length of the last robot link. So that basically changes the mapping between the robot's action and their effect. So the conclusion is that the policy is able to kind of adapt to different robot embodiments and able to converge to a good performance. So here is a quantitative result. Yeah, so actually on the right is a very strong baseline that is optimal action that is optimized in simulation and is optimized actually for each individual ropes. So we manually measure the rope parameter and then model it in simulator. But as you can see, it still kind of results in pretty high error. Like I think it's on average about 10 centimeter error, which really highlights the large sim to real gap for this task. Where our algorithm is able to achieve relatively good performance across all the scenarios that we test on. So finally, in order to kind of test the generality of this kind of iterative residual policy framework, we try to test the same framework on a different task, right, which is the class placing task. So in this task, we try to swing a class and then want it to reach to a target configuration. And again, the target pose is defined by 9 different key points on the class. And again, the algorithm does not know the physical parameter of the class. So it still need to adapt online based on the visual observation. Okay, so here is the 2 typical strategies that the system learned as we observed. So at the first step, the system will use the same action regardless of the class and the goal conditions. And then you can see that in the first case, the class actually land too close compared to the goal configuration. And then in the second example, the class actually folded up due to the high density of the class. So based on this observation, the policy will actually adjust their action differently, right? So in the first example, the policy will increase the stroke in order to swing the class further in order to getting closer to the goal. And in the second case, the policy actually chooses to decrease the speed in order to prevent the class fold by itself. And this process will repeat until it converges or reaches the goal. So typically for this class placement task, it takes about 3 steps to converge. So as you can tell, this formulation of iterative residual policy is actually a very general formulation that is applicable for most of the repeatable tasks with complex object dynamics, right? So here I highlight repeatable because this system do require that it can be reset during the different trials in order for it to work. And I think the most important lessons we learned in this iterative residual policy framework is that instead of trying to directly learn the full dynamic model that's mapped directly from action to the trajectory, what we can do is instead learn this delta dynamics model that actually learns how the changes in action will result in changes in the trajectory. So this delta dynamics is actually much easier to learn and also potentially generalize a lot better into noisy real world dynamics and also different object physical properties. So that is actually most of my talk. And I think here is a summary slide. If you want to have one sentence summary or takeaway from this talk, I hope you can remember that the importance and the benefits of incorporate dynamic action in deformable object manipulation tasks. And the reason is that by using dynamic manipulation, we can leverage the accelerations, the action, or in general, the dynamics in the system in order to kind of get more controls over the total degree of freedoms of the objects. which is particular the fundamental challenge for deformable object manipulation. And if you care about how to make this dynamic manipulation system work, here are some lessons that we learned from our projects. For example, we can use action primitive in order to reduce the complexity of learning action sequences, or we can use iterative residual policy in order to handle the complex object dynamics, and also potentially better handle sim-to-real gaps. And that's the end of my talk, and happy to take questions.
Yeah, that's a very good talk. If you have any questions, I think, yeah, you can raise your hand here or maybe line up by the microphone, and we'll have to repeat it for the people on Zoom. Yeah, so first question.
Thanks for the great talk. I was wondering, how did you address the out of plane portions of the rope while you swing the rope up?
Yeah, okay. So the question is that how we handle the out of plane motion for the rope. That's a great question. I think we actually do not actually explicitly handle that. We test the rope swing action, and we observe that it's mostly in plane. And if we really want to achieve certain 3D goals in order to, we can rotate the base of the robot in order to achieve like other planar motion. Yeah.
I'm curious, where do you think is the most difficult part, and like what's the limiting part? What's the part that's limiting the performance? Is it more understanding the state of the system, coming up with a policy, or something else?
Yeah, so the question is that which part I think is the biggest limiting factor for the whole system performance. I would say that there's a lot of things that can be better. I think the hardware is kind of limiting. If it can reach higher speeds, then I think the Flingbot, for example, will have better performance. But I do feel like the state estimation, or like the perception algorithm that's able to kind of estimate the state and also represent the goal configuration for different class. I think that is another thing that I feel really limiting our current system. So for example, in the last project, we actually simplified the state estimation by just tracking key points, right? We're tracking the tip of the rope or the corners of the cloth. But if you're handling like a shirt, pants, their configuration space is much bigger and maybe cannot be really simplified with a few key points, and they may have self-fold cushions. So I think if we really want to handle like in the wild cloth manipulation, all those other challenges we need to handle.
So for the Flingbot, when generalizing from the rectangular towels to the t-shirt, what were you treating as the corners? Was it sort of hand-coded, or was it?
Yes, so the question is that for Flinkbots, when we generalize from rectangular cloth to t-shirt with general garments, how we're treating the compute the corners. Actually, the answer is that we do not explicitly detecting corners for Flinkbots. Actually, the system learns well to grasp, and actually most of the time they don't grasp corners because they didn't learn this optimal policy where the corners are not accessible. But because it doesn't really explicitly detecting corners or manipulating corners, so it can easily generalize to different shapes.
Thank you for a great talk. I'm curious about the iterative residual policy.
Mm-hmm.
How hard do you think it would be to start advancing to 2 targets in the same stroke?
Okay, so let me repeat the question first. The question is that for the iterative residual policy, how hard it will be to extend it to reach 2 goals with 1 stroke? That's a very hard question. I think, yeah, I actually never really think about it. I think this is probably pretty hard and maybe requires some reformulations of the problem, but I will definitely think about it. It's a very interesting problem to think about, yeah.
Well, I think for that one, you could probably dynamically replan. That's possible.
Yeah, I guess the one of the challenge I think about now is like how the system even know whether that 2 goal is reachable with 1 stroke. I think that's probably the first thing the system needs to identify. And actually, I kind of don't know how to solve that problem. Yeah.
Well, actually, that brings me to my question, because this is basically trying to close the loop with the dynamic action. And the fact that a lot of these dynamic primitives are primarily sort of open loop and primarily also mostly 1 step. You can learn for a future demonstration from the past demonstration, but you cannot close the loop during execution. And so what do you think can be done to close the loop during execution? For example, let's say in sports, you see like a pattern baseball is to react to the ball.
Yeah, so the question is that can we do better? Like, so most of the dynamic action that I showed today is pretty open loop. And the question is that can we do better on like doing closed loop controls for those dynamic actions? I think definitely yes. I think that's definitely a very interesting direction. But I do feel that it requires a lot more requirements on the hardware. For example, the inference needs to be faster, and it probably also requires some other sensors like tactile sensing in order to get those fast feedbacks, or something that cannot be directly captured from the visual data alone. Yeah.
Thank you.
Mm-hmm.
Thank you very much.
Thank you.